see that, right? It just takes 1 second to go live on the other side. Okay, should be live. See that, right? God, I need to mute it. I don't know how to do this otherwise. And then what's the time of the day? Okay. I think my phone, is it ready at the time, Matthias? Do you know? Is it exact time? I don't have my phone with me.
1 minute, 1 minute to go.
I mean, I want to start
Oh,
today.
now it's 3 p.m.
Okay, now it's okay, great. So let me welcome back everybody to the online SPICE-SPIN+X seminars that we lead here in the Spin Phenomenon Disciplinary Center by myself, together with Gary Neves and Angela Wittmann. Unfortunately, I forgot we have this old slide that doesn't have her name there. With Martin in collaboration with the SPIN+X Collaborative Research Center, led by Martina Schliemann, Burkhard Hildebrands in Kaiserslautern, and by my colleague here, Matthias Chloe, in Mainz as a co-speaker. This is a Zoom web seminar, as you all know. Please write your Q&As or in the chat, and it's also live stream at the same time in YouTube, and it will be immediately, of course, in YouTube available. Today, we actually want to show you that this is the last one of this summer. We will have a break in August, and we will resume in middle of September. So please look at because there's different workshops that are being involved, and we will have quite busy time with workshops here that we don't typically do seminars at the same time. And then so just keep that in mind. But it's my pleasure to welcome Liza Herrera Diez as the last speakers of this series for the summer break. She's a researcher at CNRS at the Center of Nanoscience and Nanotechnologies. She's a doctoral student. Well, she did her physics studies in the National University of Cordoba, but not Cordoba, Spain, but Cordoba, Argentina. Okay, understood that. Yeah, it's just clear from her accent, and I understood that. And so she's a doctoral student at Max Planck Institute, so it's the research, and works quite extensively on the main world dynamics and multifunctional devices, particularly using Magneto-ionics and interface engineering to discover new magnetic phenomena. So with that, I'm going to stop sharing, and I'm going to ask Liza to please go ahead and start your talk, and we're going to mute ourselves here and to give you the progress with that. And yeah, looking forward to your talk.
Thank you. So is all right from your side? Can you see
Perfect.
everything?
That's good.
Okay, wonderful. Okay, well, first of all, thank you so much for this invitation. I'm glad to be here today to give this seminar. So we were just discussing that how nice this series of seminars is, and how important it has been for people, and not just because of COVID, but just because of the value it has for people that were not even able to travel before COVID. So it's a great service to the community. So I really bravo for this wonderful initiative. And then, as we said before, well, you cannot stop now. So you have to continue. It's really great. So, so today I would like to tell you a bit about Magneto-ionics. So, and how we can use Magneto-ionics to control magnetism. So I will show you a bit of an overview about what is being done in the literature at the beginning. So all the kind of different things that are done right now, and then I will focus on our own results towards the end of the presentation. So let me start by telling you where I am right now. So I am at the Center for Nanoscience and Nanotechnology in Palaiseau in France. So that is in the southern part, well, outskirts of Paris. So we have a very nice building. We have moved here 5 or 6 years back, and I am in the nanoelectronics department. And the nice thing is that now we integrate the campus of the Paris-Saclay University, which it's a very stimulating environment. As you can see here, we have our friends from Thales nearby and École Polytechnique. So it's we're really much closer to everything, and then especially to people doing spintronics in the Paris area. So it's a very nice place to be. So well, that said. So I want to start by the motivation of why do we want to control magnetism with gating at all, before even talking about magnetoionics. So then, well, there's a lot of what it's being done in spintronics that it's directed towards applications in memory architectures. So we know there are different prototypes with different degrees of technological development. Definitely the front runner SCT memories, but also SOT and something that we know since a while, the racetrack concept with domain walls or skyrmions. But the VCMA type of memory, which is voltage control magnetic anisotropy based, is really gaining attention for a number of reasons. So then, first of all these technologies have points that can be improved or should be improved to make it to a more performing type of product. And we can find different things, like, for example, there are, oh, it doesn't work. Why? Oh, there, sorry. So yeah, in particular, for example, SOT that requires a larger, to improve charge to spin conversion, or field-free switching, or in the case of the racetrack, for example, to better control the pinning and motion of domain walls or skyrmions in tracks. But in general, one of the important points, and then in line with everything that we know is it's one of the most important social problems that we're having, which is reducing energy consumption. That is an important point for any of these prototypes. So then this is really where electrical control of magnetism can make a difference. So we want to have, in particular, lower writing currents for these magnetic memories, but at the same time, we don't want to lose in terms of robustness of the magnetic state. So we don't want to reduce, for example, anisotropy to be able to switch it better, and in the end have a memory that does not really stand temperature fluctuations, for example. So this is really where voltage control of anisotropy could give us, could be a game changer, because we could, with the same material, with the same device, having a local gate, we could go from a state which is easy to switch with a low anisotropy, and then once the switching is done, then we switch it back to a hard magnetic state, let's say, which is very robust against thermal fluctuations for storage. So then this is why we want to control magnetism with a voltage. And this also extends, for example, to, of course, to domain wall and skyrmion dynamics that we can control also by defining pinning sides or pinning potentials with a voltage. So that said, so how do we control magnetism with a voltage? So there are different avenues that we can take. So in principle, it could be charge effects, which we know well from field effect transistors in nanoelectronics. So then we have our material of interest, an oxide with a high dielectric constant in a counter electrode. And then if we apply a voltage across this oxide, then we'll accumulate charges at the surface of, in this case, our magnetic film, which is our material of interest. And the magnetic film being a nanostructure, so it will be extremely sensitive to what happens at the interface, well, as we know very well, in particular, for example, perpendicular anisotropy, that we know that is something that, that comes from the interface. So then if with this charge accumulation at the interface, strong changes in the magnetic properties can be induced. And this is very interesting. And then, but also it has the advantages of this type of device which are the high charging speed because it's electronic, and also it's more compatible with conventional electronics. However, if we want applications where we need non-volatility of this gated state, then this is not the way to go, because this is volatile. So it's a charge accumulation. We switch off the gate voltage and the effect goes away. So, and this is also limited to the top interface. So this is where we accumulate charges. And we know well that for spintronic systems, we care a lot about the bottom interface with the substrate, because the substrate most of the time is a heavy metal material, which we're going to need to use for SOT or for DMI in particular. So then we also would like to bias this interface. And then this is not something we can do with charge effects. And this is really where ionics comes in. So in ionics, then we use a similar structure. The only difference is that this oxide, it's now a high ion mobility oxide. So it's a material where ions can easily diffuse. So then here we're going to use an electric field, so a gate voltage, not so much to induce charges at the surface of the magnetic film, which will of course happen, but to move ions in the oxide. So then once these ions move towards the magnetic film or away from it, then they will induce large changes in the magnetic properties. And the good thing is that this is non-volatile. So once these ions move, they sit somewhere else in the magnetic structure and they just stay there. So that is one of the advantages with respect to charge effects. And being the case that we are moving these ions across the magnetic film, we, as you will see later on, we will be able to bias also the bottom interface and not just the top interface. So these are really the advantages of ionic effects. But of course, it has its downside as well. So the speed is limited by ionic diffusion. So then if we want something fast, we're not going to be using ionics. So we're going to be using charge effects. And also, as you will see, sorry, my phone's ringing. So also, we will see, as I will show you later on, the effects that we look at here are very much related to the chemical states of especially the metals in the magnetic film. So then reversibility and cyclability are things that are very much affected by chemistry, and this can be detrimental for certain things, and especially needs to be very well understood in order to really use this for applications. So before I show you more about ionics, let me give you a quick overview of things that have been done with charge effects. So here there is an example: tantalum, cobalt, iron, boron, hafnium oxide. So this is, you will see hafnium oxide a lot today because this is a study that we did in our lab. So we like to use hafnium oxide a lot because it's a material that is very well known from the memristor community, but then I will get to that in a minute. So here, hafnium oxide is used just as an oxide and not as an ionic conductor. And here we could see, we could change, we could go, as you can see here, the black and the blue and the red curves. So here you go from an in-plane magnetization to out-of-plane magnetization, switching from +2 to -2 volts. And what we did with this was to have fun with this device and then apply a constant magnetic field out of plane and then switch the voltage up and down between +2 and -2. And then with the Kerr microscope, we could see how the magnetization was following the direction of the EC axis. So then in principle, you can switch the magnetization just by using a gate voltage with charge effects. So then there are these very nice studies from the several groups in Grenoble. So in this study, they could show that they could switch on and off skyrmions in platinum cobalt. So and then I said earlier that for DMI, it will be good to be able to bias the bottom interface. However, we know also that DMI depends on the asymmetry between the two interfaces of our magnetic material. So then, in principle, changing the top, inducing some electrical changes in the top interface can obviously also contribute to a change in the DMI. And this has been measured by also the group in Grenoble and the scientists in Japan. And then they could really see that a modification of the DMI was possible with charge effects. So now let me go to finally to ionic effects, which is what I will be discussing today. So I want to start by breaking this out into the different geometries for devices that you can have. So you can have solid state devices, which is the little cartoon that I've been presenting so far. So this is very similar to what you have in charge effect based devices. So here you replace the oxide by this by another oxide that is has ionic conductivity. For example, here we see this work from MIT using gadolinium oxide. So then this is definitely more compatible with applications, and it has obviously all the perspectives for miniaturization, because this is standard lithography process. You can make any device that you want like this. However, I mean, this is what you want for applications for sure. But as I said before, there is a lot that needs to be understood about the mechanisms. Where are the ions going? How are they moving around? And if you want to do this, there are other devices that are more adapted to that. So one of them is ionic liquid gating, which is what you see here in the center. So in this case, so here is one of our films. So then here, for example, you see cobalt and boron, hafnium oxide, which is here used as an ionic conductor, and then this ionic liquid. So the ionic liquid is literally a liquid that you put on top of your sample, but it doesn't have a solvent. So it's like a molten salt. So it only has positive and negative ions. So then if you place this between two plates of a capacitor, and then two plates, and then you apply a voltage, what will happen is that ions will migrate to the two plates, and then they will form a layer of ions that is on top of the surface, in this case, of the material of interest. And then the advantage of this is that although the ionic liquid itself, it's pretty thick, it's microscopic, actually what you care about when you want to calculate your electric field is the distance between this layer of ions and your surface. And that can be very small. So it's typically considered to be 1 nanometer for each one of the plates. So then the effective distance is considered to be 2 nanometers. So then you can apply, let's say, 4 volts over 2 nanometers, which gives you a pretty decent electric field to work with. And so then this is extremely easy to do. You just put your liquid on top of your sample and it works. So then if you would have to build a solid state device that can stand very high, such high electric fields, you probably have to work a lot more on your device. And it's not only a simple design, but also it does not break in the sense that it doesn't have a breakdown voltage like you would have in a normal solid state gate. So here, there's no electrons moving in the ionic liquid. So then if we stay with voltages below what is called within what is called the electrochemical window, that means that we won't have any electrochemical reactions happening in the ionic liquid. So then in principle, there's no reason why it will break. It does not break, and you can make the device as big as you want, and it will still show the same properties, which is a difference with the solid state devices. The bigger you make it, the higher the probability that there will be some pinhole, some defect somewhere that will break your gate. So, so this makes it particularly interesting to study, for example, techniques like to study magnetoionics with techniques like XPS, X-rays, BLS, some techniques that need a relatively big chunk of material to get a good signal. So then this is really what you want. Another important point about the ionic liquid is that the ionic liquid itself does not participate in the ionic process that modifies the magnetic properties. So here we have the hafnium oxide, which is really the material that has mobile oxygen inside, and it's that oxygen that's going to move to the cobalt and boron. The ionic liquid itself would stop at the interface and will not diffuse into the stack. And this is a fundamental difference with people doing electrochemistry, which is the third type of magnetoionics designed that can be used. So in electrochemistry, you really have a solution in which you have active ions inside, like the ions from your metal as well, and then you can deposit them, you can oxidize them, and redilute them into the solvent, and then this is really an active exchange of matter between the solvent and your magnetic film. And then this is really used to go more in depth about the electrochemical reactions. And this is very useful, once again, to understand what happens, what are the energy barriers, the type of chemical reactions that can happen. So this is also an extremely powerful way of studying magnetoionics. So what I'm going to show you today is here, what is in the, well, you don't see my pointer, but what is here in the center. So ionic liquid gating. This is what I'm going to show you today from our own results. Okay, but before I do that, I want to continue showing you a little bit of an overview with some nice things that are in the literature. And then, so we're moving now from, let's say, talking about ionics to talking about what kind of ions are we talking about. So most of the time we see oxygen ions moving in the system. So oxidation driven or oxidation or reduction driven by a voltage. So one of the pioneering works was done at MIT, so with gadolinium oxide. So then you've been seeing this picture since the beginning of the talk. So then here what they did is to grow different layers, because I mean, if we're assuming that with a voltage we can oxidize or reduce what we have in our stack, then they could grow different layers, saying, well, let's make an interface with pure gadolinium that is thicker and thicker next to the cobalt. So then that should be similar to what should happen with a gate, if that is really the case. And then they looked at what it does to the magnetic properties. And then they picked one, which is the 0.7, and then they applied the voltage to make this layer thicker or thinner. And they really retrieved what they had in the grown samples with thicker or thinner gadolinium. So this was really showing that this oxidation, an oxidation front in the gadolinium oxide, could be controlled by voltage, and also they were using also temperature to help this process. So then we were inspired by this work, and then in our case, as I will show you later, we could see in a platinum cobalt system with hafnium oxide, we could measure it by XPS. We could measure the binding energies of the cobalt, and we could really see that the metallic peak of the cobalt was reducing a lot after 4 minutes of gating, and also a satellite peak was showing corresponding to oxidation. So then we could really confirm there was an oxidation. And then I will show you later on that we did similar experiments with cobalt, iron, boron. And then once again, we could see by XPS how the iron and the cobalt was evolving into an oxidized state. And not only that, but also we could measure the oxygen, where we could see that there was an additional oxygen peak. Let me see if I can show you the pointer. So then here we have a big oxygen peak at the beginning on the as-grown sample, and then when we apply electric fields, and we see that there is a second peak that is really growing a lot, and then this is oxygen that was introduced in the system with gating. So then we could see that there was another type of oxygen that was growing because of the gating. So once again, showing that some oxygen activity was happening in the system. But there's not just oxygen. So the MIT group has shown as well devices in which there is a hydrogen based process. So then they started off with cobalt oxide, and then they proposed that the water from the atmosphere could dissociate, and then that there could be a proton diffusion into the layer. And then there is the hydrogen that's actually coming to reduce the cobalt oxide into cobalt, and that's how they go from oxidized to reduce through proton diffusion. And what is important about this is that something that is very accepted by now is that all of this oxygen as well, very much, is that there is a very important interaction with the water from the atmosphere. So then they made it very clear here that there's a strong influence of the water, because here they need the water to dissociate at the interface to get these protons inside. So it depends a lot on how the humidity of the atmosphere. And then recently, the group in Barcelona, so then they work more in this electrochemical approach that I was talking about before. So then they could show the conversion between cobalt oxide and pure cobalt with the associated changes from paramagnetic to ferromagnetic. But then they could do it as well with cobalt nitride. So then here, the difference is that the transport of ions is based on nitrogen diffusion. And they could show that the nitrogen transport seems to be more homogeneous and that it requires less activation energy than for oxygen. So it seems that there is really also a lot to be done in terms of what ions are used for this. So then we're not limited to just oxygen. And also another thing that is important to know is that this is not only in ferromagnets. So that we can find examples of magneto-ionic control in other types of magnetic systems. In particular, for example, here is synthetic anti-ferromagnets. So then this is done by a group in Halle. So then they showed before this is a synthetic anti-ferromagnet. So then they have these two layers coupled by the ruthenium, and they could show in earlier work that. Actually having this anti-ferromagnetic interaction, it's incredibly beneficial for the domain wall velocities in the system. And then that it depends on the degree of compensation. So here what they did is that they simply took that type of system and then they put an ionic liquid on top, and by changing the degree of oxidation of the top layer, they could actually control the degree of compensation between these two layers. So, and then this could create, as you can see here, really large changes in the domain wall velocity. So then it was it's really nice to see of variations of hundreds of meters per second, which is very nice. So and then this was also shown in natural ferromagnets. So then this is gadolinium cobalt, and this is once again the MIT group, and they could show nicely that they could go from cobalt dominated to gadolinium dominated magnetic moment domination, let's say, and then they could see that they could change the compensation temperature, the magnetic moment compensation by gating, and this was done again with hydrogen mobility. So. So, well, this is really a very short overview because there is a lot being done in magneto-ionics, but I wanted to show you not only just my own work, but also kind of a big picture of what is going on right now. So let me focus now on our work. So here is platinum cobalt hafnium oxide. I told you before, we're using hafnium oxide because it's known to have a high oxygen mobility. So here what we did is to put the ionic liquid on top, we apply the voltage, in this case is a negative voltage, and then we remove completely the ionic liquid. So it's a non-volatile effect. So then we can really afford to just take the gate out of the device completely and then use it for measurement or for patterning or for anything else. So here what you see is that on the left is the loop that we get out of plane for the S-Chrome system, which does not show perpendicular anisotropy. While after 1 minute of gating, we can see that it nicely goes to a perpendicular state with very nice domains. So I told you already about oxidation, but it's nice to see that studies were done much before any of this magneto-ionics was being done. And then the group in Grenoble, well, one of the groups in Grenoble was showing that for platinum, cobalt, alumina, then they could see how the perpendicular anisotropy would depend on the degree of oxidation at the cobalt oxide interface. So this basically shows that there is a window of optimum oxidation that gives the highest values of PMA. But if there is too little oxygen, or if there's too much oxygen, then PMA will be lost. And this is really something we related to immediately, because we said, well, we have an ascorone film that if we apply a negative voltage on the top electrode, that means that anything that is negatively charged will be pushed into the magnetic film. And it's highly likely that that is some oxygen kind of species, oxygen or OH, for example. And then that would end up oxidizing the cobalt. And then we see that we go from this under-oxidized to this optimally oxidized state. And then we get PMA. So we do see very well how the gate is driven the oxidation and promoting the system to PMA. So let me see how okay. So I show you already the XPS evidence of the cobalt oxidation. So we also see the evidence in X-ray absorption spectroscopy. So what is interesting from XAS is that we don't see satellite peaks for the cobalt oxidation. We just see an increase in the amplitude, which is, it goes in line with oxidation, but it's not a brutal oxidation. I mean, and we know very well the system has PMA, it's still very much magnetic, so then it's a very, very gentle oxidation. But then here we could see as well that the platinum was showing some changes as well. So then this was, I mean, there was not a lot to analyze about this, but at least we could see, well, something is happening to the platinum. We might have a shot at reaching the cobalt platinum interface and maybe seeing what happens to DMI, which is something I mentioned at the beginning that is of interest. And so then I will not go, I mean, I will not explain much about DMI to this audience, but just in case, so then we have the Heisenberg exchange interaction that wants all the spins to be aligned in one particular direction. But then in the case of the DMI, it's an antisymmetric exchange interactions that it would like to have the spins oriented perpendicularly. And then this creates stabilized structures that are helical and especially that they are chiral. So then this could be probed with Brillouin light scattering by measuring the non-reciprocity of the spin wave propagation that I will not go too much into detail, but in principle, because of this chirality, we could see a shift in this in the frequency of the spin waves, let's say winding in opposite directions. And since DMI is setting one of the a chirality, then the appearance of this frequency shift, it's a signature of DMI, and this is how we can measure it. So then we did measure it in this system, and we could see that as a function of the gating time, we could see a weakening of the DMI. So this is something that was also evidenced in Tomeu motion. So then also together with our friends in Salamanca, they did some measurements, and then they did some magnetic simulations, and then it was really the changes that we're seeing with gating were corresponding to variations in DMI and also in anisotropy, but in particular in DMI. So what can we learn from this? It's that, well, I mean, we're introducing ions into the system. There is the part about oxidation that is very much related to the perpendicular anisotropy. But if the ions go deeper into the layer, and if they intercalate between the cobalt and the platinum, there's a high chance that we will be losing the coupling between the cobalt and the platinum. And then that ions can only decrease DMI. And this is really why we think that the DMI is just only decreasing in as we put more and more oxygen inside. So, well, I wanted to talk to you now about another system. So I think I'll go a little bit faster here so I can reach the last part. So once again, interesting to look at ferromagnetic layers that are on top of heavy metal substrates. So here we have cold iron boron on tungsten. And what we find here is that we do the same experiments as I showed before. We apply the voltage to our ionic liquid, but we don't find anything. Neither positive nor negative voltage would do anything to this sample. So this is what we learned. We know that tungsten is polycrystalline. It's in the beta phase. So it's not quite the same as we had before, an entirely amorphous system. So what we see here is that we cannot induce PMA with oxidation in this system. So, so then what we thought is that, well, that's why people anneal it to get PMA, so then that you can get this crystallization of the cobalt iron boron and this nice quality interface with the tungsten. So we did that, we got PMA, but what is interesting is that this we did XPS on the samples before and after annealing, and then we could really confirm that the peaks look the same for iron and for cobalt. So there's really no oxidation here. It's just the effect of the crystallization, just the effect of the annealing. So this shows that to get between these two, there is a transition between in-plane to perpendicular anisotropy. So this is not related to oxidation. So this is quite different from the system that we saw before. So, well, so in this system, I mean, we cannot generate PMA with gate-driven oxidation, but we can certainly kill it. So this is really what we do here. We apply -3 volts, we get oxygen into the system, and then at some point it just goes in plane. We get a similar effect for DMI, it just decreases. We get a decrease in magnetic moment. This is very much in line with an oxidation. This is confirmed by XPS. Here, I mean, you can see the first two spectra that I showed you before and after annealing, but then after voltage, you can quickly see how the metallic iron disappears and transforms into oxide, same for cobalt. And what I said before, the appearance in the oxygen spectra of, well, the increase, let's say, of this peak that can be related to, of course, the oxidation of the metals, the oxygen in the oxide, but also to OH in the system. So we can really see that we are pumping oxygen into the system. So, so then, well, what is important to think about here is that, well, both this system and the system I showed you before are not reversible. So everything that I've shown you so far is not reversible. You cannot bring it back to the original state. You can just go only in one direction. So I will not talk about much about the platinum, but at least I can tell you here it's simple to understand, because here we're looking at a crystallized system. So then if we think that in an amorphous system, ions can go anywhere. In a polycrystalline system, the ions will mostly go, if they have to diffuse, through the grain boundaries. So then if we're limited to ionic transport in the grain boundaries, then that will limit a lot the mobility, and especially, I mean, we might put ions in, but it will be hard to get them out. We already have an asymmetry in the voltage that we have to apply to get ions in or to get them out. So then this makes it very hard for to recover the original state. So then, so what we thought is that, well, let's maybe anneal at the lower temperature so we can have a compromise between magneto-ionic performance and the magnetic properties, but we couldn't really succeed. I mean, we could see that, I mean, at some point you have to anneal, and even if you anneal at lower temperatures for very short times, it will still not be enough. So then it seems that crystallization is not really good friends with ionics, because you have a harder time moving ions back and forth. So then I told you already at the beginning, so reversibility is an issue or can be an issue for magneto-ionics. So we really wanted to see reversibility in cobalt iron boron systems. So so we used here in this case a tantalum buffer layer. Everything is it's amorphous, and then here we found well, something that I already showed you. We start with an under-oxidized state. If we keep applying, in this case, we use -2 volts. We keep pumping oxygen species into the system. We will go eventually towards an optimally oxidized state. But then, which is something I didn't show before, in the same system, then you can push it further and then over-oxidize it. So, so then we define these different regimes, and then you can see here that you can, as a function of the gating time, you can go up from 0 remanence to 100% remanence in the PMA state, and then back to 0 remanence. And then this is, of course, faster if you use a higher gate voltage. But you can already see from here that the branches going up and the branches going down do not really have the same slope. So then you can really have a hint that things are not quite the same from under-oxidized to PMA and from PMA to over-oxidized. And this is something that it's important to mention because we can see, especially when it's related to reversibility, we can see a lot of things in the literature where we say, well, with this oxide is reversible, with this oxide is not reversible, with this oxide is not working at all. So then we, up to this point, we were saying, well, maybe, I mean, it's, there is an issue with the type of oxide. And then we try to do reversibility experiments in this system. So here we did it in regime 1. So here you can see we go from the initial state to something that is more perpendicular, not even the full perpendicular state. And then we applied 4 volts, which is pretty much the limit of what the ionic liquid can do. Even for very long times, there's hardly any reversibility. So that was not very nice. So then we said, well, this is probably, again, the hafnium oxide interface, we should maybe be using another oxide. But then we looked at the regime 2. And regime 2 is perfectly reversible. So then we can go very nicely from in-plane to out-of-plane magnetic anisotropy. We can cycle it. So then here we realize that it's much more complex than just something related to that particular oxide. So then it's really the different types of chemical reactions that can happen, even in the same material, that can give you reversibility or irreversibility in the same material with the same oxide and the same magnetic film. So our interpretation of this is that when we go from the under-oxidized state to the optimally oxidized state, we start with something with metallic cobalt and iron. So then this is pretty easy to oxidize. So then any oxygen that will come in contact will bind to, in this case, I make the example with iron because it's an iron-rich film. It will bind to the iron, and then the iron will transition into metallic iron to iron 2+, which is something we saw before in the XPS. So this has a relatively high energy barrier. So this is a proper change in the oxidation state of the iron. And then, so then from then on, so you can keep adding oxygen to this iron 2+. But before it gets to iron 3+, which is at the end of the line here, it might go through a state where it's actually iron 2+, still iron 2+, but surrounded with more and more oxygen with a different chemical environment, but still iron 2+. And then this is probably why this process here is easier to reverse. So it has a lower energy barrier to bring oxygen back and forth between these two states than here, because here you really have to convert iron 2 into metallic iron. So I'm not saying it cannot be done. It's just that it will not happen at the same gate voltages that this. So then here we're limited by the voltage we can apply, and then we could, with the same voltages that we do reversibility here, it's clear that if this is the case, it will not be possible. One other thing that makes us think that this is the case is that we know that if we overdo the oxidation here on this state, which is it's already in plane, but then if we keep going with the oxygen, at some point it will not be reversible anymore. And then this is where we think that we actually go to iron 3. So that it's a similar situation as here, a higher energy barrier, you cannot go back. So this is really our interpretation right now. I mean, we're looking forward to XPS results to confirm these changes in the oxidation, but this is really what is important about this is that you can have the same material, but you can be talking about different types of reactions or chemical interactions in your material between your metal and the ions, and this could define what you can do with a certain voltage that your gate can give you. So I think I'm towards the end. So yeah, so then this is all I had to show you today. So I hope I could give you an overview of the topic, and also to be able to show you a little bit what we're interested in, which is to learn more about the mechanisms of magnetoionics. And in terms of our work, I hope I could show you that we can induce changes in perpendicular anisotropy and in DMI with using ionics, that it's better to use amorphous materials because crystalline materials might get in the way of ionic diffusion. And the reversibility and cyclability are very much affected by the different chemical reactions that can happen between the ferromagnetic layer and the mobile ions. So then I hope I could show you the Magneto-ionics has a lot of potential for spintronics and for energy efficiency and new functionalities. For example, of course, we are all thinking about neuromorphic applications, and then these systems are very much adapted to a lot of different applications in synapses, etc., that we're very much considering at the moment. But one message that I want to pass is that Magneto-ionics means chemistry. So then we really have to think, yes, we want to do some nice physics and spin-dependent phenomena, but here there is chemistry. We have to take it into account, and working with people that do chemistry is really a very important aspect of this research. So I would like to thank all the people that were involved in this. In obtaining these results. So the people at C2N, including the PhD student Rohit Pasha, who is the one who did most of the work of the recent work, and all the collaborators around the world, and obviously funding from France and also from Magnify, our IT end. And I would like to thank you for your attention.
Thank you, Lisa. That's a fantastic talk. So we have a couple of questions. The first one is from Shan Hook. Go ahead, please ask your question.
Okay, can you hear me?
Yeah, we can hear you. Thank you.
Okay, wonderful. Okay, so wonderful talk. Thank you very much for this nice talk. Question about this hafnium oxide. First, probably because of this high K, you're using this hafnium oxide. Or is that because of good oxygen mobility? Is that the reason why you're using hafnium oxide? And related with that, you probably know that if you dope with yttrium, then which has a different valence than hafnium, 3+ rather than 4+, then system tends to have oxygen vacancy, so that oxygen mobility can drastically increase. So I wonder if if you can dope with yttrium, whether you can have a kind of better kind of oxygen motion. And second question, somewhat related with this is, have you thought about energy? How much power you really need to switch this magnetic state? Because what you're doing is, rather than electric field, actually, it is more or less current, ionic current. So that probably there is kind of energy loss. So in that sense, have you thought about maybe the whole community may think about this issue, how much power, electric power is needed to switch the magnetic state using this ionic motion? Thank you.
Okay, well, to your first question about ion mobility in hafnium oxide, it is true that there is a lot to be done. Actually, I'm starting to connect more and more with the memristor community because they know all about this. And indeed, doping of hafnium oxide may be a very interesting avenue to increase mobility. But also another important thing is the counter electrode. So I didn't say much about this, but then we're using ITO as a counter electrode. So I think that probably the ITO is also contributing to the oxygen transport in the hafnium oxide. So then that we will be, we know, for example, that if we apply high voltage for quite a while, then we can take the ITO electrode out, and then we can see that it's completely transparent. So it sort of dissolved into the ionic liquid. So then it might be that we are actually increasing already our mobility in the hafnium oxide because we're pumping oxygen from somewhere else that is going also into the hafnium oxide. But it is definitely there's definitely a lot to be done and to learn from the memristor community to increase mobility, like, for example, doping. Yeah, absolutely. And then the second question, Can you remind me? Sorry.
Energy. How
Energy,
much
yes,
power is needed? Yeah.
Yes. So I think it's important to see. I mean, when we do ionic liquid, we can see like almost even a few microamps sometimes. But as you say, I mean, this is not electronic. I mean, these are ions moving, but this is mostly the ions from the ionic liquid. So then there is definitely this ion mobility that shows up as a current. But we have also made solid state devices that I haven't shown you today, but then we were trying indeed, I mean, to compare now on the same samples, solid state devices which don't have the ionic liquid, and then see what kind of, for example, power consumption is needed in different geometries. But then in solid state devices, we don't see a lot of current. I mean, for example, if it's a good sample, then it's just nanoamps. So then, yeah, I mean, if, as I said before, if we want to do applications, we don't use ionic liquid. We want to go with the solid state device. But the variations are so small in terms of the oxidation that happens at the interface that it doesn't really show up as a current additional to the leakage current that we could have that could impact the power consumption. We really see only nanoamps, a few nanoamps.
Right. Excellent.
Okay. Thank you.
Thank you. So let's Zong Wang. Maybe you have two questions. Can you mute yourself? Yeah, there you go.
Thank you very much for a nice talk. I actually have two questions. The first is that in your experiment, how do you confine the ionic liquid between the electrode and the hafnium oxide layer? And my second question would be, just imagine that you don't use ionic liquid. What would happen if you just apply electric field through the hafnium oxide layer? Is it possible to directly drive oxygen from hafnium oxide into a sample? Yeah, thank you.
Thanks. Well, regarding the design of the device, it just holds by surface tension. So then we have the film, we put this very viscous liquid, like a little droplet, and then you have another electrode, which in our case, it's a glass plate coated with ITO, with the indium tin oxide. So it's a relatively transparent, relatively conductive. You do that because we want to do microscopy as well. And then if you put it on top, then it just holds. Even if you do experiments vertically, then the device would just hold together. So there's really not much. That's what I would say. It's just so simple. You put the droplet, you put the other electrode, and you're ready to go. So not much to do there. And can you remind me the second question, please?
Yeah. Maybe you already mentioned something like that, but just to keep it clear. So what would happen if you don't use ionic liquid?
Okay. Yeah. Yes. So you still, well, first of all, the hafnium oxide that I've shown you on our films, this is done by our collaborators in Singulus, and they deposit this typically 3 nanometers of hafnium oxide in situ by sputtering. So then this hafnium oxide is not very good, let's say, in terms of electrical properties. So actually, we can very well bond across it or on top of it, and then access the metallic layer underneath when we want to do transport. So this is not a very good insulator. So what we do when we want to get rid of the ionic liquid and when we want to work with solid state devices is to add another hafnium oxide on top that is grown by atomic layer deposition. So then in that case, you have a very good hafnium oxide with very good insulating properties and a good dielectric constant and all that you want in an oxide in a gate. So then this is really what you do. And then this will create an electric field that would make the ions move across the stack. And then another important thing is that we're probably using a lot of this oxygen of the bad hafnium oxide that moves around because it's non-stoichiometric, etc. But we should not forget about the influence of the humidity. So then we get a lot of oxygen from the atmosphere that probably dissociates on the top electrode and then enters the film and is driven across the layer. So it is not only the oxygen that is already in the hafnium oxide itself, but it's also an interaction with the atmosphere.
Okay, excellent. Thank you. So, Sino, Matthew, can you ask a question? Unmute yourself if you can. Yeah.
Yes. Thank you for the exciting talk. I have two questions. The first question is how deep this oxygen going into the film, let's say iron, and second one is how fast after removing the ionic liquid, how fast the magnetic measurements were done.
Okay, so the first question is how far the ions go into the layer?
Yes.
Okay, so
sorry, I mean, because there was a background noise.
Okay. So we have data that I didn't have the time to discuss today, but we have our collaborators in NIST in the US who did PNR, so neutron scattering, and they could reconstruct the profile of the, let's say, a depth profile of the film before and after voltage. And actually, I was extremely surprised to see that we see changes all the way up to the interface between, in the case of the platinum cobalt, between the platinum substrate and the silicon oxide substrate. So then it goes all the way into the layer. So this is something that we're also investigating. Now we have some TEM data as well that shows that ions are really going deep into the substrate. So not only, they don't stop at the interface with this heavy metal substrate or any other substrate. They really go all the way up to the silicon oxide.
And bringing back will be really difficult in that case. Bringing back the ion would be difficult, I think.
Yeah, I think that's one of the things that can happen. That, for example, if you have some material that can capture a lot, this, for example, platinum has a lot of affinity with hydrogen, for example, and then if you happen to have a substrate that really will capture your ions, you'll probably have a hard time getting them out. So this is something that we're investigating right now. I mean, what happens with these ions that don't come back? I mean, where do they get stuck? So, yeah. I don't know, you had the second question?
Second question is about the magnetic measurements. After removing the ionic liquid, is it stable for a long time or?
Yeah, I mean, for example, especially the perpendicular state is extremely stable. So I have, for example, the samples from this Cobalt paper that was published in 2019. The measurements are from, like, I don't know, 2018, 2017. I still have perpendicular samples that I used to check the contrast in my Kerr microscope. So there are some other cases where there can be evolution, definitely, in particular sometimes in the intermediate states. But this, I mean, it depends a lot on the history, on what voltages you apply before and after. It can depend on a few things, but the PMA state, at least, it's extremely stable. And then you can also stabilize very well the in-plane states. And it's mostly about the intermediate states that we're thinking about. Sometimes they evolve a little bit in general towards PMA. But yeah, there is a good stability of at least the PMA state. I mean, for us, I mean, sometimes we send samples for XPS and then it gets there next week and then the person measures it like weeks later and it's still fine. So
yeah. Okay. So let's ask Max. Thank you. Max, go ahead and ask your question, please.
Hello. Thank you very much for your talk. I wanted to ask about the model that is behind this electric field and the anisotropy. So in your case, you apply the field, you promote the oxidization. That's more or less okay. But there is a model, for example, of Wonderland that relates magnetic anisotropy with filling of the band haven't you seen any examples of this ionic gating effect with positive ions that do not create oxidization of the material? So you just create a positive layer of ions without oxidation?
Well, this is a little bit what is done in the case of charge effects. So then this was really the first measurement on the gating of magnetism. Actually, there was a really nice study, once again, from Institut, so where they could show that they were using the ionic liquid. And as you say, I mean, the ionic liquid stops at the surface of your material. It doesn't go through. So then there, you just use it to create an electric field. And then in their case, they could nicely show that, for example, in iron platinum, if there were, I don't remember exactly what the positive or the sign was, but let's say if you apply a negative voltage, you increase anisotropy. And then they went there and they looked at theory papers where they could look at the band structure and say, yes, I mean, you should be increasing anisotropy with band filling, let's say. But then they said, well, if we want to confirm this, then we should take a material where this should be inverted, where the bands don't have the same slope. And then for the same voltage, we should get the opposite. And actually, they did this with iron palladium. So then they said in iron palladium, this is inverted. And they really saw the inverted effect. So they could really show, well, this comes from the band structure. But this is charge effects. So absolutely, I mean, in charge effects, then it all comes down to the band structure.
Okay, thank you.
Thank you. And lastly, Sayed, would you like to ask your question?
Yes, thank you. Thank you, Liza, for a very nice talk. I have a quick two questions. One is, do you lose some magnetization when you inject your oxygen in your cobalt or boron? And the second question is, if you use hafnium oxide overoxidized, instead of making oxygen from the top, so it will help like if you over-oxidize and under-oxidize hafnium oxide during growth? So is it help, like does it help for your experiment? Thank you.
Yeah. So for the magnetic moment, yes, I mean, we have seen that magnetic moment can decrease a lot with oxidation. So with both the cobalt and the cobalt iron boron that I showed before, we could see a decrease, and then we measured it with squid, and then we could see a decrease in the magnetic moment. So it was not at some point with our collaborators from NYU, we measured, we wanted to measure to see if there was an exchange bias at low temperatures because of cobalt oxide, but we couldn't see it. So then, I mean, it was not, as I said before, there was not a huge oxidation, but we could definitely pick it up from the in squid. So there is really a decrease which goes together with an oxidation. And then to your question about the hafnium oxide, yes, I mean, I guess you could use an hafnium oxide that is slightly more oxygen rich, but you also don't want to. Well, yeah, I guess if you over-oxidize your interface, you can always try to bring it back. But once again, so it's not just the oxygen in the hafnium oxide. There is an exchange with the atmosphere. So then you can always pick up more oxygen from the atmosphere. So it's actually funny because for us, you can see very clearly that, for example, in the experiments where we annealed samples, so if you take the annealed sample out of the oven and you try to do electric field, it doesn't really work that well. So because it comes from the oven, so then all the water is out. But then if you leave it sitting in air for a few days, then it will be very efficient. And then this I know from other labs as well, that like there's this sort of black magic on the devices that sometimes you blow on it and it works better because you just got hydrated. So it's not just the oxygen in the hafnium oxide that will do everything for you. Yeah.
Thank you very much. Thank you.
Okay, excellent. So I think that's the conclusion. I'd like to thank all the 100 of you who showed up between here and the online format on the streaming site.